So I'll talk about a project I worked on during an internship at Microsoft Research called zee-not. And this is a new zero-knowledge compiler that makes three main contributions. So first of all, it does some really aggressive automatic optimizations. And we'll see that this actually makes some pretty interesting applications performant enough for practical use, kind of for the first time. zee-not has built-in support for distributed environments, so it tries to make the process of writing distributed applications more transparent for developers. And finally, zee-not allows developers to write zero-knowledge enabled code in a high-level language. It uses C#. So the hope is that this kind of opens up this previously niche cryptographic primitive to a much wider audience of developers. And we implemented 6 applications in zee-not, and the goal here was to sort of look for things that have a really broad appeal, but also illustrate this tension between privacy and integrity that zero-knowledge proofs can help out with. So we looked at applications like a crowdsourced traffic map, retail loyalty cards, collaborative recommendation systems, and things like that. And now we can take a closer look at one of those applications, specifically crowdsourced traffic maps. So for those who aren't familiar with this type of application, I'll play a short video that was produced by Waze. Can you turn the audio on?
Just drive with the Waze app open, and you're already contributing a ton of traffic info that helps your fellow drivers. You can also actively report events you see while driving. All hands-free, of course. Waze's big brain rounds up all the real-time info shared by the community and gives you the fastest route to your destination, every time.
All right, so this is a really cool app, and a lot of people already use Waze. I think it has several million users, and it was recently acquired by Google, I believe, within the past year or two. And so let's take a closer look at how we might actually implement that. So basically, as the video said, these little ghost icons on the left, these are the Waze users. As they're driving around, they keep the app open, and the app pulls location data from the phone's GPS. Right? And then Waze sends all that continuous location data up to this centralized server. They call it the big brain. And the server is going to do some crunching over all this GPS, all these coordinates, and compute some routing information that it can send back to the users, and they can avoid traffic jams and speed traps and nasty things like that. But let's think about some adversarial situations here. So what happens if this server has some malicious intent? Well, the obvious thing is it poses a privacy concern for the people who use the application. Because they're constantly sending their coordinates to the server, it can build a pretty detailed profile of where they've been and learn quite a bit about them. And that's obviously not a great situation. We could also have a malicious user. And this raises a different kind of concern. It's more of an integrity concern. So say we have a user who is really concerned about their privacy. And they might try and get these nice crowdsourced traffic maps for free by kind of sending garbage GPS coordinates up to Waze and getting the service sort of gratis. This is obviously not in the best interest of Waze. They don't want this to happen because if everybody did this, there would be no app and everybody would suffer. So this crowdsourced traffic app really illustrates this fundamental tension between privacy and integrity, which is the kind of thing that we're hoping zee-not will be able to help out with. Right? Zero-knowledge proofs offer a really attractive solution to resolving this kind of tension in realistic scenarios. So let's see how we would use zero-knowledge proofs to re-implement an application like Waze. First of all, we wouldn't send raw location data directly from the users to the centralized server because that obviously violates their privacy. Instead, we might have them enter into some kind of a protocol where they exchange with each other some kind of opaque location data. And then over that opaque data, and I'll get to what that means in a second, they do this computation to build some aggregate statistical data about what the traffic looks like on a map, which they can then send to the server along with a zero-knowledge proof. And the point of this proof is that it demonstrates to the server that this traffic data that they're getting from the users is truthful in the sense that it's what Waze intended the users to compute from their GPS coordinates, right? So that resolves the integrity concern. The second benefit that this brings is the zero-knowledge part. And of course, this allows the users to make this demonstration in a way that doesn't require them sending their raw location data directly up to the server, and that eases the privacy concern. So what do we mean by opaque location data? Well, you can imagine taking a segment of a map, or a portion of a map, and partitioning it into segments, and partitioning the roads into segments, and assigning each segment a unique identifier. The users could then give each other Shamir shares of the segment that they're currently in, and perform computations over that, right? And so we actually implemented sort of this core functionality of the Waze application in zero-knowledge. And we did this on two state-of-the-art zero-knowledge compilers that both came out within the past year. So these are both products of Microsoft Research. We looked at ZQL and Pinocchio. And when we looked at the performance, what we saw was that if you just use ZQL or Pinocchio on their own, you couldn't actually do this fast enough to send this off to a phone and realistically support the desired functionality, right? So just to process a single GPS reading, you have to wait around for a really long time. But so we started doing this by sort of taking the app and by hand translating into either Pinocchio or ZQL, sort of as the situation, as it was appropriate. And when we did that, we saw that we could actually get some timings that made the application feasible. So why is there such a contrast in the performance between these two compilers? Well, each of these compilers, or backends as we call them, have significantly different execution models. So ZQL works by taking a source program or a query, as they call it, and translating that into a sort of a pure functional subset of F#, which they compile to the common intermediate language and execute in .NET. Pinocchio takes a subset of C and compiles that into a circuit representation, and then you can just sort of evaluate the circuit on its inputs and produce a zero-knowledge proof on the side. And each of these computation models works really well for some types of operations, but not as well for others. And this is what zee-not uses to get the sorts of gains that I talked about earlier, right? It sort of picks and chooses the correct backend for a specific application at the right time. So let's take a closer look at how that works. I'd said that in zee-not, developers can write their code in a high-level language. We support C#. And the hope is that by allowing this, developers can use zee-not on just a small fragment of their overall application and sort of integrate that into a larger, possibly existing code base in an environment that they're familiar with. Once zee-not begins to compile an application, it begins optimization by doing a performance analysis. And it builds what we call cost models. And these give it some information about how expensive a given fragment of C# will be when it's translated into zero-knowledge. With the cost models, it can then basically build a large mathematical optimization problem, and the solution tells it how to best translate C# into either backend. And it can then go ahead and compile down into binaries, and if the developer wishes, can do automatic tier splitting to send the right parts of the code off to different hosts as the application needs. Okay, so let's see how we allow people to write zero-knowledge in C#. And we'll do that by looking at a really short function from the Waze app that I discussed earlier. And there are a few things to point out here. So first of all, programmers specify exactly which portions of their code they want to be translated into zero-knowledge. And they do this using a really simple kind of functional annotation. They just say zero-knowledge begin or zero-knowledge end, and that tells the compiler where to focus. zee-not supports translating link expressions into zero-knowledge. And link stands for language integrated queries, and it's a part of C# that kind of looks like SQL. And so it's a kind of declarative way of doing computations. Then if the programmer wants to do automatic tier splitting, they can provide annotations with location directives at the granularity of functions that tell the compiler where to send the various functions in the code. Finally, to enable the most aggressive optimizations that zee-not allows, programmers can annotate inputs to zero-knowledge regions with sizes. So that would represent the maximum size of the enumerable that region is going to operate over. let's talk about cost modeling. I'd said that zee-not uses cost models to do optimization. And the point of a cost model is to take a specific fragment, excerpt of a larger C# program and characterize how efficient that will be when translated to either backend. So it basically takes two things: the size of the input that C# will operate over, and some micro-operation timings, which I'll get to in a second. And it gives hopefully accurate prediction of the execution time of that C# in a particular zero-knowledge backend. And so here's a fragment of one of the cost models that zee-not actually generated. And as you can see, the input is the size of the data it's going to work on, as I said. And all the rest of the symbols here are, they represent the micro-operation timing. So they basically reflect how much time an add operation or an equality test or an exponentiation will take when executed in zero-knowledge. And we get these by basically profiling on the platform that we're targeting with the compiler, and then just substituting in the constants for all these symbols. So how do we build these cost models? Well, I'd said that ZQL takes a program and generates sort of a pure functional representation of it, basically a sequence of map, fold, and find operations. And for this sort of thing, we can always bound the number of operations that's in one of these expressions as a function of the size of the list that it's operating over. So we basically do symbolic evaluation over a polynomial domain. And the polynomials that we're operating over they characterize the execution time of the computation so far. So at the end, we have our sort of closed form expression that characterizes how long the ZQL operation will take. Pinocchio compiles things into a circuit, and it's a lot easier to characterize the runtime of a circuit. It's a set of gates and wires. You can basically sort of statically ahead of time build some expressions that say how long the circle will take to evaluate based on the number of gates, the type of gates, and the wires in there. So let's look at translation and tier splitting. So once we have these cost models in hand, we need one more piece of information to do good translation into zero-knowledge, and that's what we call a performance profile. This is basically a developer-specified configuration that says for each tier what the relative cost of computation and data transfer is. Once we have this, we specify a pretty large nonlinear optimization problem that we can solve using something like R Mathematica. And the solution to that optimization problem tells us exactly which backend to send each fragment of C# in the zero-knowledge regions to. Right? So we can compile binaries from that, and the only thing left to do is split this up into tiers. So for those who haven't seen like a tier splitting compiler before, the basic idea here is to take our original program, partition it up into little chunks, and then only send the relevant chunks to the hosts that actually need them. While in the meantime inserting automatic code to do data marshalling, transfer, and synchronization. And the way that zee-not actually does the splitting and then inserting the code is pretty interesting from kind of a pure engineering perspective. We take a really minimalistic approach that allows the compiler to get away with doing just a little bit of program analysis to figure out dependencies and so forth. I don't have a lot of time to get into it, but we do write about this in the paper. I believe it's an attached appendix, so please read that if you're interested in this sort of thing. Okay, so how well do we do? We ran each of those 6 applications that I had mentioned earlier in 3 configurations. We either sent everything, all the zero-knowledge regions to ZQL, to Pinocchio, or we used the solution that zee-not came up with in its optimization. And we did a lot of experiments, and we generated a lot of charts, and there are quite a few in the paper, and we write about them in length, so please read it, but I'll just kind of go over some of the main points here today. So if we look at that customer loyalty card application that I had mentioned, and look at the amount of time that it takes a client, so that's somebody's cell phone running this loyalty card app, to process a single shopping transaction, we're plotting this against the number of purchases that person has made in the past. This loyalty card is sort of tracking. And we see some interesting things. So ZQL doesn't do very well in this application. There's basically one operation that's really expensive for ZQL to do, and it's located on a, in a loop on a hop path. So this actually causes ZQL to time out on pretty small inputs, just 100 purchases in the history. The other two solutions do a lot better. They scale to all the data sizes that we tested, but you can see that the zee-not solution scales much more gracefully, right? It's got a smaller constant on that linear growth. And so this basically just shows that the cost models zee-not built did a good job identifying this expensive operation and sending that off to Pinocchio instead of letting ZQL handle it. If we look at another application, we implemented a network intrusion detection system, or sort of the core of it, and we look at the server's throughput. That just means the number of alerts per minute that the server can verify. We see something that's even more interesting. So here, Pinocchio does a lot better on the server, right? It can handle way, way more alerts per minute, but you can also see that it times out, or it just sort of dies out at about 400 bytes of network trace leading to the intrusion. The reason for this is that the client end of the Pinocchio solution is a lot more expensive than the other two, and that's what's actually timing out, so the server doesn't even have anything to verify at that point. And what this demonstrates is that global optimization problem that zee-not solved effectively identified this trade-off in some server performance for greater scalability across both tiers, especially on the larger data input sizes. So I won't walk through any more graphs. There are a lot more in the paper again. I'll just sort of summarize the main points of the rest of the experiments. When it came to scaling, so how well did zee-not cope with larger data sizes, we found it did a lot better, up to, it could handle up to 10 times more data on the inputs than the other two. In terms of raw performance, I think it generally did about 5 to 7 times better. In one case, it got up to a 40x improvement, which was awesome. And proof size is kind of interesting. So Pinocchio is a snark. It actually generates constant size, really small proofs. I think they're like 288 bytes. So zee-not's never going to do better than Pinocchio when it just comes to proof size. But it does do a lot better than ZQL. And as we saw, Pinocchio doesn't do as well for performance. So what zee-not offers is the ability to still reduce from the size of ZQL's proofs, but without sacrificing its superior performance on some operations. Okay, so to wrap up, I talked about how zee-not uses cost models to enable some really aggressive optimizations. I showed how developers can write zero-knowledge enabled code in C#, and hopefully that will allow non-experts to sort of play around with this primitive. I discussed how zee-not automatically supports tier splitting, which makes writing distributed apps a lot easier. This is really important for zero-knowledge type applications because this tension between privacy and integrity generally arises when you have code running on different hosts owned by different people. And finally, with a lot of experiments, I showed you that these optimizations actually make possible, we think for the first time, some really interesting applications. Thank you.
Thank you, Matthew. Questions? All right, I've got one. From a software engineer's perspective, how cognizant do they need to be of ZQL or zee-not or Pinocchio's constructs on the back end? Maybe ask another way. How hard is it to write good code that doesn't turn into like degenerate performance case?
Right. So the point of the global optimization is that it shouldn't really be possible to write degenerate code in zee-not. I think it's actually really easy to write it if you're just focusing on Pinocchio or ZQL. But we found the cost models were really accurate, generally maybe 10% prediction error on those, which amounts to like a couple tens of milliseconds absolute timing. So yeah, it really shouldn't be easy to write degenerate code in zee-not.
Please. Hi, I'm Eran Tromer, Tel Aviv University. Wonderful work, and I'm just wondering about what part of C# being supported, in particular, how about runtime determination of array accesses, loop indices, loop length, pointers, and such.
I'm sorry, could you repeat that? There was some noise coming from the hallway.
Does it support all of C#, or is it, does it inherit Pinocchio constraints in terms of pointers, loop length, and array indices?
Right, so we only support link operations for translating to the backends, right? So we don't have to worry about pointers and everything like that. I mean, I guess you could, try and sneak a pointer in a lambda or something, but no, we don't handle those cases.
Thank you.
Yeah.
All right, let's thank our speaker.